Okay, lecture 4 and the Doppler effect. Please be sure to look at the YouTube video about the Doppler effect. I think it really explains the effect quite well and explains why the pitch changes when we have a moving reflector. And so again, please make sure that maybe if you want to stop at this point, go back and look at that YouTube video and then come back to this lecture. I think that would be a good way to move forward. The difference between the transmitted and the reflected frequencies is called the frequency shift or the Doppler shift. A positive frequency shift occurs when a reflector is moving in a direction that is towards the transducer. The negative frequency shift occurs when a reflector is moving in a direction that is away from the transducer. And you can calculate this shift by using the Doppler equation. One of the acronyms that we can use to remember what our profession prefers as far as the color of the shift would be BART or BART, meaning that blue is away from the transducer and red is towards the transducer. So that is how our ultrasound community would like the colors to be reflected. A couple of things when looking at the Doppler equation on page 129 is that we see the Doppler shift will be in Hertz, meaning that we can hear the Doppler shift. And that's because when you subtract the transmitted frequency subtracted from the reflected frequency, this number is going to be about 1/1000th of the operating frequency. So we're going to drop from megahertz or beyond human hearing, and we're going to drop that down into kilohertz, which will be now into where humans can hear it. So one of the things that we'll want you to do is to really get used to hearing what these sounds, concerning pathology, what they're going to sound like. Of course, you know that if we have a positive Doppler shift, it's going to be a higher pitch. If it is a negative Doppler shift, then it's going to be a lower pitch. And that will also tell you if it's moving towards or away. And then we know the assignment is blue is away and red is towards. Remember that while we do calculate the frequency shift or the Doppler shift, what we're really concerned with is the speed or the velocity of blood. That is really our concern, because we know that we equate speed with pathology. But again, the frequency shift, while it does measure that, we also calculate the velocity. How Doppler works is because the incident sound reflects off the red blood cells that are in the blood. Red blood cells are very small, only about 7 microns. Because of that, we call them natural Rayleigh scatterers, and they are very small when compared with the incident wavelength. While performing the Doppler effect, using high frequency transducers may give you a stronger Doppler signal, but remember, you're going to lose attenuation. Higher frequency is like our sprinter, and you're going to lose the energy very quickly, so it will not be able to go deep into the body. So just remember that you may have a trade-off between improved resolution and penetration, and this is, a trade-off you're going to have to make all the time. But again, because you're using higher frequency, you're also going to have more scatter, and scatter is a form of attenuation. Another thing to recognize is that in the Doppler equation, we're not actually using the Doppler angle, but we're using the cosine of that angle. So as the Doppler angle increases, the cosine of the angle will decrease. meaning that the Doppler angle and the frequency shift are inversely proportional. The Doppler angle must be known in order for us to get accurate velocities. In echocardiography, a 0-degree angle is always assumed, and that means it would be perfect speed calculation. While in echocardiography, we are able to get that 0-degree angle and again calculate perfect velocities. In vascular, we're not able to get that 0-degree angle. So we're going to have a relationship with the cosine of the angle and then its accuracy towards the speed. We're going to talk a little bit later about how to get the most accurate speeds when working with a vessel or with a moving part that we cannot get a 0-degree angle from. But here's some things to note for now. There is no Doppler shift at 90-degree angle. The cosine of 90 degrees is 0, and if you plug that into our Doppler formula, you'll see that that means we multiply everything by 0, which gives us no Doppler shift. To look at the accuracy of the angles that you'll be using, look at table 4-17, which gives you the cosines of the angles. And as we just said, the 90-degree angle has a cosine of 0, so again, you would have no shift. Most of the time, we'll be using a 60-degree or less cosine or angle, and the cosine you see there is 0.5. So again, the speed would have to be multiplied by 0.5, and then you would get your accurate speed or velocity. And you see at 0-degree angle, we get a perfect velocity because we multiply everything by 1. There are some devices that are, or Doppler devices that are non-directional or unable to tell us if it's a positive shift or a negative shift. But for us, that's not going to be very useful. So we need to know the direction of flow. So Doppler devices use phase quadrature to determine whether there's a positive shift, meaning a flow towards the transducer, or a negative shift, flow away from the transducer. So again, adding that term to your vocabulary, or knowing that how does Doppler determine direction? It would be using phase quadrature technology. There are two ways of obtaining a Doppler signal. One is continuous wave and the other is pulsed wave. We've been talking about pulsed wave, or we will be talking about pulsed wave here in a few minutes. But continuous wave Doppler devices have two elements. So when you're holding that in your hand, there will actually be one element or crystal used by the system to constantly transmit sound into the patient's body, and the other crystal is constantly receiving sound. Now, because of that, there is no image, there's no time for us to use what we call a pulse echo technique to actually get an image. So this, while continuous wave is constantly sampling all of the blood, we're going to get very good velocity data, which, as we've talked about before, we need that to know how much or what kind of pathology that we have going on in our patient's body. But again, no image, so we're not always sure where we're at in the patient's body. So continuous wave devices have no range resolution. We don't know how far away these reflectors are, and we only get a spectral Doppler waveform. Our technology today will allow us to freeze our pulse echo image, and then we can apply our continuous wave Doppler to give us kind of an overlay of where we're at in the patient's body. But again, it's a frozen image, so if we move our hand slightly or adjust the depth slightly, it's not going to be reflected on your image. So we'll have to go between pulse echo and continuous wave kind of rapidly. As you see on this slide, the dilemma is when there are several vessels within the same sample volume, because continuous wave will sample everything that it touches, and we don't have a way to resolve that. There's no dampening with continuous wave transducer. If the sound is being transmitted continuously, dampening is not needed. And this also means that there is the continuous wave device is putting sound into our patient's body 100% of the time, and the duty factor calculation would be 100% or 1.